Okay, let's continue with our slides. So this part will be related to the detection and also the bit error rate for these different modulation scheme for the bandpass modulation. And I don't think we will spend too much time on the derivation, but we will try to utilize it, okay? So let's take a look. So as you have seen earlier that for the detection or modulation, demodulation scheme in digital communication, there are two main types. Okay. Well, in other textbooks, maybe there are different other types, but these are the, let's say these are the two main types that we focus. One is called coherent detection. Okay. So for this type of detection, you need to be able to synchronize the phases. I think we should say synchronize or match the phase of the carrier, which in this case is cosine omega 0 t, and the received signal, okay, which is RT, okay. And you saw earlier in previous the lecture that if you don't synchronize these phases well, then instead of having the maximum values at the output of correlator, maybe you have zero, you know, for example. So that means that in coherent detection, you need some sort of like a phase locked loop or a phase estimation block. Okay. And for the other type of detection scheme, this is non-coherent. So for this type, that you don't need to know any phases of the carrier at all. Okay. So it's simpler in a way. For non-coherent, you can use either the, I guess in a way you can use the analog approach like envelope detection, or that was for ASK, or you could use the some type of low pass filter followed by envelope detection, you know, for FSK. Okay, but for some system like FSK, if you remember, for the non-coherent detection, you could also use the correlator structure as well, but you need twice the number of correlators. Okay. So, but yeah, but that would work for FSK. But that type of correlator structure for non-coherent approach, that doesn't really work for ASK or some other types of modulation scheme. Okay. Anyway, so in terms of vector plots or constellation diagram, um, if we consider the detector uh, in the perspective of the vector plot, okay, we can consider what is called minimum distance detector or receiver, meaning that, you know, as we illustrate or we look at each symbol or each pulse in terms of vectors. So let's say that here we transmit with two symbols, one is S1, one is S2, for example, okay. And on the receive side, the receive signal is always corrupted with noise. Let's say this is the AWGN channels, okay. So what we have at the receive signals in terms of vectors is they just scatter around, you know, what we transmit, right? Depending on how large the noise is, if the noise is, it has a high variance, then this circle becomes large. If the noise is small, then the circles or the scattering becomes smaller. Okay. So in a way, in terms of the vector domain, the detector aims to decide whether S1 or S2 has been transmitted, and we try to reduce the bit error rates in the system. So that's always the goal. Okay. So if we consider the detector as a minimum distance detectors, okay, uh, this is when probability of one symbol and the next symbol is the same. Let's say probability of bit 1 is equal to bit probability of bit 0 is equal to probability of bit 1, for example. Okay. In general, actually, when we say minimum distance detector, it means if we are given a received a vector like r here, okay, we make decision rule as follow. We select or we make decision on the transmitted symbols or transmitted vector that gives the minimum distance between received vector and the symbol vector. So basically, we just compute this distance and see which one is lowest. Okay. Of course, you say that in terms of the structure that we saw earlier, we use the correlator. Yes, you're right. But I'm saying that it is equivalent to looking at it in terms of the minimum distance, approach. Anyway, okay. So if the probability of bit of one symbol and the other symbol is the same, then we can look at the detection as the minimum distance detection. Okay. But in general, when when this assumption is not right, is not met, we have a more generic detector, which is called a maximum likelihood detector. So minimum distance detector is considered like a subset or a type of maximum likelihood detection. So in minimum distance detector, you try to minimize the distance, right, between receive vector and how do you call it, and the symbol J. Okay, but for maximum likelihood detector, their goal is to maximize the PDF of of Sj given R. This is PDF. Okay, so this is maximum likelihood detection. For example, if you only transmit 1 or 0, the goal is the detection is to maximize the PDF of 1 given R and also PDF of 0 given R. Okay. Actually, I should write it as probability because this is the, yeah, I think I should write as probability. Yeah. So we try to maximize the probability of transmitted bit is 1 given what we received. Okay. So that's what they try to maximize. Okay. But when we have this different assumption, we can have minimum distance detection as a subset of the maximum likelihood detection. Okay. So maybe it's a more like a probabilistic point of view. Okay. But minimum distance is more like a geometric point of view. Okay, so if you take a look in in terms of the vector plots, okay, we can view the problem as like this. S1 and S2 are the transmitted symbols or the vectors. Uh, what we can do is we can look at the decision in terms of decision region and boundary. Okay, for example, if in order to obtain the decision boundaries, okay, we can obtain it from uh, draw a line, okay, perpendicular to another line that connects or connecting symbols. Okay, so decision boundary can be obtained from can be obtained from draw a line that is perpendicular to another line connecting symbols, okay, particularly the symbols that are next to each other. Okay? For example, if we have these two symbols, S1 and S2 that are next to each other, we can draw this line first to connect them, okay, and then we can draw another line, which is this dotted line that is perpendicular to this connecting line. I call this as a connecting line, okay. So this decision boundary will divide between the two decision region. Okay, this will be decision region number. Oh, I wrote it here already. Maybe this is called decision region number 1. This is decision region number 0. Okay. It means that if so here we can divide the region of decision into different region or different colors, which is yellow and blue, right? So if R falls into whichever side, we make decision accordingly. Okay. So if R falls into whichever region of decision, okay, so we make decision accordingly. Okay. Meaning that if R falls here at that moment, you, in a way, from the vector point of view, you can just make decision to bit 1. If vector R at that symbol or that bit time falls into this region, you can just make decision to 0. And this concept is used in order to compute the probability of bit error or probability of symbol errors for the non-binary system. We will not go deep into it because it will take a long time to derive. But I just want to show this concept to you. Okay, so it means that for various types of modulation scheme, you can draw some type of decision boundary like this. Okay, for example, this one is easy, right? Decision boundary is perpendicular to the connecting lines here. So this is the decision boundary, right? For if there are 4 symbols, this will be connecting line. Sorry. Okay, if there are 4 symbols here, okay, these the dotted lines, they are the connecting lines, right? And we have to draw lines perpendicular to these connecting lines. So these are called decision boundary. Okay, and we can construct like a different decision region. Oops, it's too. The color is too. The color is too light. Yeah, then we can divide into this the region. Okay. And so on. Okay. Or if it's the 8 PSK, okay, so you can connect these neighboring symbols like this. Just connect them first, and then we can draw this the dotted line as the decision boundary, okay, which are perpendicular to the connecting lines. Okay, so if you look any textbook, if they look at how to derive the bit error rates formulas, this is approach they look at. Okay, they look at probability of error in terms of each region and they average it. Okay, but we're not going to look into it because like I mentioned, it takes time. So here we can have like different region for decision, like this. So in general, there will be M region for memory modulation scheme. Okay. Okay. Similarly, if you take a look at like 4-QAM or 8-QAM like this, 4-QAM is similar to PSK. So that's all you have for region. Okay. For 8-QAM is a bit more difficult. 8-QAM, you notice that M is equal to 8. Okay. In general, for QAM, if M is 2 to the even number, okay, then we call a rectangular constellation. Okay, but 8 is 2 to the 3. For this type of QAM, you will not have a exactly rectangular constellation. You have like a more, I don't know, it's the jacket rectangular constellation. Okay, so let's take a look here. So in order to determine the decision region, we have to connect the lines first between neighboring symbols. So these are the connecting lines. Okay. Okay. And let me change to the red color for the decision boundaries. So this line is one of the decision region, no, the decision boundary, right? To connect to intersect with these connecting lines, and they are perpendicular to connecting lines. Okay. But then we also have this line between S6, S2, S5, S1, S3, S4, and S4, S8, which we need to draw the, how do you call it, perpendicular line. So here we can draw like this. Actually, it's not difficult. We can draw like this. Oh, it's a bit difficult to draw for me. Yeah. Yep. And so this is, so all the red colors here, they are the decision boundaries. Okay. Let's call this decision boundary. Okay. And then what are the decision region? Because M is equal to 8, so we have 8 decision region. Okay, let me use light blue. Okay, so we have this as one region. Okay, this is another region. Okay, so if the vector R falls into this region, you make decision accordingly. Okay, like this. Okay, so there are four regions here, and then 4 more are outside. Or let me change color maybe, so that's a bit easier to see. Which color should I change to? Blue, orange. Okay, let's do orange. So this is like the remaining 4 region. Okay. So this concept they are used for probability of error computation. Okay. Okay. So this is it. Okay. Okay, so now you look at the probability of errors now. For the binary case, it's very simple. Because they are they resemble the baseband approach. But for the non-binary, like I mentioned, they can be derived from this type of decision region. because each region represents probability, but we will not derive it. We will just look at the formula and how to use it. Okay. So let's look at the bit error rates for bandpass modulation scheme. Okay. So first of all, let me see. So for if we consider the bit error rate for the antipodal pulses means the pulse that have a opposite sign. Okay. And when you draw in the vector diagrams, this is the what you have: two vectors with the opposite values. Okay. So for this type, during the lecture before midterm, we already saw that the bit error rate is in terms of this type of formulas, which is the Q function of square root 2 EB over N0, where EB represent the energy of each symbol or each bit or each vector. Okay. Equivalently, if we consider because this is in vector plot, so if we consider the distance between the distance between these two vectors, let's call it D12, okay? This D12 is basically just equal to 2 square root EB, right? If you look from the diagram, this is 0. So square root B on each side. So the length is just twice square root EB, right? So it means we can write these formulas in terms of distance as well. Okay. So we can express 2EB as this 2 square over 2, which is 4EB divided by 2, which is 2EB. Okay. Yeah. So these two formulas, basically they connect between the SNR value and also distance in terms of vector domain. So let's take a look how to derive each bit error rate, but we will look at the binary case instead. Okay, so let's take a look. For example, BPSK. For BPSK is the same as the one on previous slide, right? Which is two vectors with energy E or the magnitude square root E, right? Or EB. And if we use this formula, we will have PB the same on the previous page, which is square root 2EB over N0, okay? I don't replace this D12 with the value from the previous slide because it's the same, so no need to rederive it. Okay. Actually, the plot of the vector is the same as polar and RZ. So you notice that the bit error rate is the same, right? Yeah, it's interesting. Baseband and bandpass. Okay. So that's one. Okay. So it is pretty much the same as polar and RZ. Okay. So the signal constellation is a tool used to compute the bit error rate. So let's take a look at the next one. Okay. Next one, ASK on off. Okay. We will start from this formula in terms of distance between vectors. So we have Q of, what is it? What's the distance here between these two? This is, I think, square root EB, right? Because this is 0, right? For ASK, you either don't send anything or you send something, right? So here, when you square it, you have a square root EB over 2N0. Okay, that's all. And for ASK, this is when consider the baseband modulation. What is it? What is it similar to? You remember? One is to send nothing, and Bit 0 send nothing, and bit 1 you send something. This is the unipolar NRZ. Okay. So it's the same formula as well, no? Okay, next one is for the orthogonal type, which is orthogonal BFSK, and this is for the coherent system. For here, the vector plots are like this. We have two vectors that are orthogonal to each other, right? And one is on frequency 1 and the other one is on frequency 2, right? Each one has energy of EB, so the magnitude is square root EB. So what is the distance between these two? Using the Pythagoras theorem, is the square root 2 times whatever of this size. So it becomes square root of 2 EB, right? So you can just replace this distance. You square it. So you have 2 EB at the top divided by 2n0. So you get a Q of square root EB over n0. Okay. So this is for any orthogonal type modulation scheme. Okay. So if I talk about some type of compared to the baseband modulation scheme, what are the type that can be used here? Well, one of them is PPM. Okay, PPM is you transmit 0 with half the bit time, and for bit 1 you transmit during half the bit. Oops. Okay, this is an example. Okay, but EB is only half of the NRZ, you know. Or you can have like this type of like they call CDMA type. Okay, for one user number 1, you send with the full bit, and then for user number 2, you transmit with like similar to Manchester, half positive, half negative. You know, these two are orthogonal because when you multiply them to each other and then you integrate, you get 0. Okay. And you can use this formula for this type of different orthogonal modulation scheme as well, even for baseband modulation scheme, or they can be used for any other types of orthogonal modulation in band pass modulation. For example, if you use the one for bit 0, you use cosine. This is just to think for fun, okay? And then for bit 1, you use a sine. Okay, we know that sine and cosine, they are orthogonal within the bit time. You can use this formula as well. So it's generic in a way. Okay, but if we focus only the passband modulation that we studied earlier, okay, let's look at this one first. So this is the type of plot that you will have. So for BPSK, this is the leftmost line. Okay, the next one is this is differential BPSK. Okay, so the bit error rate, the graph is slightly inferior. Okay, but it's probably useful for its application. Okay, normally when we look at the bit error rate, in terms of bit error rate, which line is the best, the left or the right? Can you guess? When we look at different bit error rate curve like this, which lines, which line is the best, the leftmost or the rightmost?
The leftmost.
Yeah, it has to be the leftmost. Okay. Well, you can look at it in terms of like this. if you look at the x-axis, which is the existing or available SNR, okay, if you only have available SNR of 8 decibel in the system, for BPSK, it gives you 2 times 10 negative 4 bit error rate. Okay, but if you use the differential here, you get what is it? 9 times 10 negative 4. If you use the system, the third line, which is BFSK coherent, then you can have bit error rate only what is it? 1, 2, 3, 4, 5, 6, 6 times 10 negative 3. If you use BFSK but with non-coherent detection, then you can have bit error rate of 2 times 10 negative 2. And if you decide to use ASK, then your bit error rate becomes 4 times 10 negative 2. Okay, so this is what it is. Or you can look from one specific bit error rate. Let's say we look at 10 negative 4 as the benchmark, okay? And it intersects each line here, right? Okay, so this one is about, let's say, 8.5 decibel. This one is about 9, let's say 9.2 decibel. This one, let's say 11.5 decibel. This one is 12.3 decibel. This is 14.3 decibel. Okay, so if you can compare these plots from the SNR axis, or you can compare them from the bit error rate axis. Okay, if you look at the bit error rate axis, okay, you find that for bit error rate of 10 negative 4, for BPSK, you only require 8.5 decibel in the system. But for DPSK, you need to have at least 9.2 decibel in the system. And etc. If you want to use BASK, then you need at least 14.3 decibel in the system for the SNR. Okay. And so it means that BPSK is a system that is more efficient. For the same SNR, it gives the lowest bit error rate. For the same bit error rate, it needs the lowest SNR in the system, right? And this difference is called gain. Okay. If someone asks you what is the gain of BPSK over DPSK, how do you answer? What's the difference? 9.2 and 8.5 between BPSK over DPSK. The gain is equal to 9.2 minus 8.5 in terms of decibel, okay, which is 0.7 decibels. Yeah. So that's what when people talk about the gain, they look at the specific bit error rate, okay, and see. You can say this is SNR gain, the gain in SNR from different system, okay. And we will compare like this for binary, non-binary, and so on. Okay. So typically, bit error rate graph is like this. Okay, the higher SNR in decibel, you have lower bit error rate. Okay. However, in communication theory, the limit is called channel limit. Okay. Dr. Lin is gonna talk about this during next lecture. From Dr. Shannon, he introduced the information theory field and also introduced what is called Shannon's limit, that says that any reliable communication with the bit error rate approaches 0 cannot happen if SNR is below minus 1.6 decibel. Okay. But for typical like BPSK, at 10 negative 5, this the SNR is at I think 9.6 decibel. Okay. So we will use the concept or the technique called error correction codes to reduce this SNR even further in the system. Okay. Oh, also I need to emphasize that to many of you are misunderstanding. When you compute the bit error rate, you need to convert the SNR from decibel to how do you call it, to the non-decibel value first. Okay. So let's come back to this example just for fun. This example say let's compare the bit error rate of BPSK with SNR 8 decibel and also BFSK with orthogonal. Sorry, this is orthogonal with coherent detection as SNR 10 decibel. Compare the bit error rate. Okay, so let's do this example for. I should quickly. So for BPSK, we will have that the bit error rate or probability of bit error of BPSK equals to Q of square root to EB over N0. Okay. EB over N0 is 8 decibel. We have to convert to non-decibel value, which is 10 to the 8 over 10 or 10 to the 0.8, which is 6.3. Okay. We don't put the decibel value in the formula. So this will be Q of square root of 2 times 6.3, okay, or Q of square root of what, 12.6, right? Okay. Okay. Let me go to MATLAB quickly to compute this Q function. So if you go to MATLAB, I can compute this from Q function of square root of 6.3. Okay. Oh, one parenthesis is missing. Okay, so I have 6 times 10 negative 3. Okay. Okay, so I have a 0.006, right? Or 6 times 10 negative 3. We often write it in exponential term like this. Okay. Okay, and next one, let's look at PB of BFSK. Oops. Maybe it's saving. Wait one moment. Uh-oh. Don't quit on me, okay? Please come back. One moment. Okay. Oops. Next one is BFSK. Let me save it anyway, just in case. Okay. This one, we use a formula Q of square root EB over N0. Okay. This is from previous slide. So we have square. Okay. So here SNR is 10 decibel, but in terms of non-decibel is 10 to the 10 over 10, which is 10 to the 1 is also 10. Okay, so this is a nice number. So square root 10. Okay, so I'll go back to MATLAB again and then try to compute it. Okay, so here I have square root of 10, right? Is that right? Yes. Okay. Okay, because this one has higher decibel, right? So this 12.6 and this is the square root 10. Okay. Okay, it's 7.82627 times 10 negative 4. So it's the 7.827 times 10 negative 4. Okay. So okay, so here it means that for these two systems with different SNR, the BFSK is, I didn't do anything wrong, right? Okay. The BFSK has lower bit error rate than BPSK. Okay? So BFSK at 10 decibel and then BPSK at 8 decibel. Why do I feel like something is not right? Yeah, something seems strange. Wait. Square root of 12.6 is higher than square root of 10. So the value has to be, so this thing has to be lower than this, right? What did I do wrong? One moment. Right? In the parentheses, that's why. So you can take a look up there. I forget to multiply with 2. Okay. Because in parentheses for Q function, if the in parentheses the value, if the value is higher, then Q function gives lower bit error probability. No. So something was wrong. Yeah, I thought doesn't look right. So it should be 1.929. 1.929. Okay. Right? Is it 1.929? Did I remember right? 1.929 times 10 negative 4. Yeah, you're right. Okay. So therefore, bit probability of bit error rate or BPSK at 8 decibel is still lower than probability of bit error rate, probability of bit error of BFSK at 10 decibel. Okay. So that's how you know like convert between SNR and bit error rate in the system. Okay. And we use this a lot. Yeah. Maybe you don't know how they come about or how the formula is computed, but at least these are the basic one. Okay? We can just look at it and then compute it and so on. Okay. And okay, so let's look at the next one. Wow, looks like I'm always delayed these days for some reason. Okay, so now let's look at the bit error rate for MPSK. Maybe I don't finish the whole set of slides, okay? But I will try to give example of bit error rate so that you understand what we are doing. So I think it's you understand it better that way. Okay, so for bit error rate for MPSK, this is of MPSK and for coherent detection, okay? If you look at the vector constellation, you see that as you increase the M value or you increase the data rate, okay, the faces the faces become closer to each other, right? And they are in the circle constellation, you know, in circle, but the faces become closer to each other, right? It means that it really reduces the noise tolerance. Okay? So you can get higher data rate, of course, but the bit error rate will inevitably decrease. Okay, so your bit data rate will increase as M increases, but it will inevitably reduces the bit error rate. Oh, no, not reduce the bit error rate. It will increase the bit error rate, which is the inferior. Okay, because if the bit error rate is reduced, it's better. Okay, so let's take a look. For MPSK, the bit error rate, if we plot the bit error rate, we will have something like this. And x-axis is the SNR in decibel. Okay, so So when you plot the bit error rate curve, I forgot to say that on the y-axis, we always plot in log domain. They call, yeah, it's the log domain values. That's why when they are small, you can still see, you know, they have the equally spaced. Okay, so this is like each decade of the bit error rate. Okay, or this is one decade or one order of bit error rate. Okay. So the leftmost one, as expected, is for m equals to 4 and also m equals to 2. It turns out that for the BPSK and QPSK, they will have the same bit error rate levels because the QPSK is just two sets of BPSK transmitted on cosine and sine separately, and they are orthogonal. Okay. So the leftmost one, they are for QPSK and also for BPSK. Okay. Then if you increase the m values, you will have the graphs, move to the right, like m equals to 8, m equals to 16, 36, 64, and then etc. Okay. So in a system, this is how we work on it. If we have in most communication system with high data rate, they can switch m up and down. Okay. So let's say that in this system, initially you are at you are very close to, let's say that, okay, let me redraw it. Let's look at a scenario. Oops. Let me use the blue colors. Okay. Okay. So let's say that if the bit error rate in the system is set as a threshold at 10 negative 4, okay, depending on the application that we saw earlier, if you remember, right? Depending on whether they are voices, they are used for real-time gaming, they're used for uh, they're used for buffer the streaming. They're used for autonomous car. They're used for system data quality control. Transmission. They have different bit error rate that you have to maintain. Okay, but let's say that we look at 10 negative 4, and at the beginning, let's say you're transmitting at this very nice bit error rate. Let me call it say 6 megabit per second. Okay, maybe because you are so close to the base station, you are so close to the router, or because the noise level in the system is not too high. Okay, so you have this at SNR. Let's say that you are at about 27 decibel. Okay, as time goes on, let's say that you have your SNR reduced from 27 to suddenly to let's say to 17 decibel. Okay, so let's say that your SNR suddenly is reduced from 27 to 16 decibel because you travel away from router, or you travel away from the base station, or maybe because the noise level or interference in the system becomes higher, right? So what do we do to maintain? Let me draw a red line to maintain this 10 negative 4 threshold. We have to maintain this because for each application, we can have lower bit error rate, which is better, but we cannot have higher bit error rate because we cannot control. So this is like an important values. Then what do we do? Because here, if we still keep the bit error rate at m is equal to 64, okay, if you take a look at 17 decibels, okay, then your bit error rate will change to, wow, over 0.1. This is like 0.3. Okay, then your bit error rate now is 0.3. for MPSK or for 64 PSK. Okay, meaning that if you want to maintain this megabit per second at 6 megabit per second, okay, so let me write it up here. For 64 PSK, okay, if you change from 27 decibel to 17 decibel, your bit error rate will increase from 10 negative 4 to 0.3, which is unacceptable, right? If you want to maintain this the quality of error in this the application, okay? So what we need to do is we need to reduce the M values. We need to reduce M in order to still have bit error rate below 10 negative 4, okay? So here we can take a look at for 17 decibel here, can we move from m equal to 64 to m equals to 32? If we do that, we have bit error rate here at 2, 3, 4, 5. 5 times 10 negative 2, which is still higher than what we want, right? So we cannot. We need to go lower. So here from 6 megabit per second to 5 megabit per second, we can reduce to this speed, but the bit error rate is still high. How about we move to here, m is equal to 16, so we have 4 megabit per second, okay? So here the bit error rate will be slightly higher, okay, at 2 times 10 negative 4, okay? So if you reduce m to m is equal to 4, m equals to 16, we have 4 megabit per second, and the bit error rate now becomes 2 times negative 4, okay? So here, depending on the system, whether they're satisfied or they're okay with this value, if they just need to be below 10 negative 4, then you need to move one further to m is equal to 8, which is the 3 megabit per second. So it's half the bit rate, half the data rate, right? Then what is the bit error rate here? So for 17, wow, it's very low. It's down here. So it's even below 10 negative 7, okay? Bit error rate even now below 10 negative 7, okay? Then you are fine. Okay? So that's what we do when we use this type of diagrams or bit error rate curves to move between data rate and so on, okay? Similarly, if you are at m equals to 8 and suddenly your SNR maybe moves to say 18 decibels here, okay, then you can move back to m equal to 16 because here bit error rate is below 10 negative 4, okay. So let's say from 17 you goes to 18 decibel, okay, then you can use m equals to 16, but you cannot use m equals to 32 or m equals to 64 because you still have higher bit error rate than the threshold in that application, okay. So it depends on the application that you look at, okay. Is this picture clear for you? Okay, these two I can skip. I just want to say here that the bit error rate for BPSK and QPSK are the same, okay. So for okay, these two let me skip. Okay, let's go to some formula summary of formula for bit error rate. So we can use these as for each type of modulation scheme. Okay, for MPSK, for m is greater than 4, you can use this formula. Okay, you see that here you have to replace m with whatever m you have, and also here we have es. Es is the symbol energy. symbol energy, okay, which is because they are k bits, so it's k times EB, okay. And you can use this for all formulas. ES is equal to KEB. Okay, for MFSK, this is for coherent detection. For non-coherent, I think they're exponential function. For MFSK, you use this formula. Okay, and for MQAM, so these two we'll use very often. For MQAM, here is already in EB, so you can use it. And L is equal to square root M, from our earlier lecture. And the last one is for MDPSK. Okay. So that's about it. Yeah, for this formula. And let me see what time is it. Oh, already 11. Okay. Let me look at the last topic called the spectrum efficiency or bandwidth efficiency between MPSK and MFSK. And then we stop and look at Simulink. Okay. So for bandwidth efficiency or eta, it is equal to bit rate over bandwidth. Okay. And this can be the bandwidth of the signal, it can be the bandwidth of channel, but generally it's a signal. Okay. For MPSK, the bandwidth efficiency is equal to K bit per second per hertz. But for MFSK, this is equal to I don't remember. I have to derive it. I think it's 2K over M plus 1 or plus 3. I'll come back to this. Let us derive first. Okay. And I'll come back to this page. I think it's M plus 3, if I remember it right. Okay. Okay. And then, okay, now let's derive for each one. For MPSK, the spectrum is just like this. If you don't use power shaping, okay, and this is just a square pulse, we have the bandwidth at RB or RS in general, because this is for symbols, okay. If this is 0, or this is the, okay, let's put this as 0, no, as a center. Okay, so the bandwidth in general W is RS, okay. And okay, and for the bandwidth and RS is what? RS is the symbol rate, symbol data rate, symbol data rate, okay, which is the data rate of bit rate divided by K, because each bit, because each symbol we send 2 K bits. Okay, so the bandwidth efficiency is eta equals to RB over W, but W is RS. This is in hertz because it's the bandwidth. So this is RS. So it's RB divided by RS. RS is RB. Oops. It's RB over K. So K goes to the top and they cancel out. So this is K bit per second per hertz. Okay. Or this is the log M base 2, same value, right? So it means that if we increase M, we have better bandwidth efficiency in general for MPSK. And then next one is for MFSK, okay? For MFSK, let's talk about the orthogonal type, okay? If you remember for MFSK, last time this is what we look at. So I will draw only the main lobe, okay? And normally we need to make for MFSK for orthogonal, the center has to differ by multiple of RS over 2. Okay, let's use the minimum one. Okay, this is for binary, so there are only 2 main lobes. But if you have multiple, let's say you have 4, this is what happened. So this is the RS over 2, okay, and RS over 2, RS over 2, okay. So this is the difference. It has to be RS over 2 so that they are orthogonal. But the way I draw it maybe is a little bit misleading, okay. RS over 2 is smaller than half the main lobe, okay. But I draw it maybe equal, maybe not so good. But in any case, so second part of the main lobe is RS. So this is RS, okay. And so in general, the bandwidth is like this. The bandwidth consists of 2 parts. One is the middle part, which is m minus 1 times RS over 2. Here we have 4 FSK, okay? So there are 3 of them, m minus 1 RS plus 2. Therefore, the bandwidth or W is m minus 1 RS over 2 and then plus RS on 2 sides, which is 2 RS. Okay. So here we will have MRS over 2 minus RS over 2 plus 4RS over 2, right? So we have MRS over 2 plus 3 RS over 2, which is M plus 3 RS over 2. Okay. Therefore, the efficiency from the formula is RB over W. So it's RB divided by this thing. So multiply with 2 divided by M plus 3 times RS. Okay. So this is RB times 2 divided by M plus 3. Okay. But RS is RB over K. So this is RB and K goes to the top. So they cancel out. So what I have is 2K over M plus 3. Okay. Let me take a look whether it's right on the previous page. 2K over M plus 3. Okay, same thing. Okay. So that's the difference between these two type of PSK and MFSK and FSK. And we can compute, for example, compare between MPSK and MFSK. Okay, let's say that we compare between various M. Okay, so for various M's, let's say that the bit error rate is 10^-5 in the system, and okay, so let's say the bit rate is 9,600. So for the symbol rate, if the binary is the same, okay, and W is just RS, right? So W is just 9,600. Okay. So if we, anyway, so we can find this or not, it doesn't matter, but we have the formula for eta already. Okay. Eta is just K. It's just 1, 2, 3, 4 for PSK. Okay. And okay, so for QPSK, if RB is 9,600, RS is RB over K over 2, so it's 4,800. W min is 4,800. Okay. And then for M is equal to 8 and 16, you can do it like this. You can find the efficiency. Okay. For the bit error rate, we just look them up from the graphs. So we see that when M increases, the SNR required in the system will also increases. Okay. On the other hand, for FSK, FSK is quite interesting actually. So let's compute. For W is, what is W from previous page? M plus 3 times RS over 2. M plus 3 times RS over 2, right? So for M equals to 2, we have 5 over 2 times 9600 times 9600, whatever it is. This is the something like 40,000, roughly, no? 40,000 hertz. Then for M equals to 4, we have, oh, wait, let me see. If we have like this, and we have like this, so this is RB over 2, and then RB and RB. Okay, so that's right. And 46 2 over 9600 is 48, right? Times 5. So it's actually RB over 2 plus 2 RB. RB over 2 plus 2 RB. So 92, 19,000 plus 96. So it's about 28,000, roughly. No? And then for FSK, 4 is the 4 plus 3, which is 7. 7 times 48,000. So this is how do you call it? So this is about 28,000 also. So quite similar. No? Oh, this is 30 something, 33 something. Okay. And then for M equals to 3, I think for M equals to 3, so you have 3 plus 3, 6. 6 over 2 is, I forget to divide by 2, that's why. So, so this will be 4 plus 3, 7, and then divided by 2. Okay, so it's 3.5 times 4,800. Okay, so this will be 12 something. Maybe 15,000 roughly. No, need to be exact. We just want to compare. And for M equals to 8, we have something like 22,000, and M equals to 16 is 36,000. Okay. So in general, tends to increase as well, but slower for for the bandwidth compared to MPSK, where bandwidth is smaller. Okay. And for eta is 2k over m plus 3. Okay. So this one will be 2 times 1 over 5. Okay. 2 times 2 times 2, which is 4. 4 over 7. And 2 times 3, which is 6. 6 divided by 11. And 2 times 4, which is 8. 8 divided by 19. Okay. So the efficiency of the FSK is not bad. Okay, it's well, it's not super efficient, but it's slowly decrease actually. if you take a look, it slowly decreases the bandwidth efficiency. Okay, but an interesting part is here actually for MFSK. Okay, so let me write down at the bottom. No, so eta seems to increase as M increases. For MFSK, eta seems to decrease, and for SNR, you require more. SNR you require more as M increases. Okay, but for MFSK, it's interesting. You require less SNR. Okay, so this is very one of the interesting point of the FSK. Although it has worse bandwidth efficiency, but in terms of the required SNR, it requires less. Because for FSK, for each symbol, you use orthogonal dimension. So you sort of like send on a separate channel, you know. They don't interfere among each other because they are so orthogonal. Yeah. So MPSK is so in a system, when we look at the type of communication system, for a system with power limited system, meaning that bandwidth, there are a lot of bandwidths available in a system. It's not expensive for bandwidth. Like in military, in space, or in some types of system. And if they require low SNR, let's say you send a system to Mars, to space, power is so important, right? Because you're so far away, you're like 1,000,000 kilometers away, but you have so much bandwidth available, you don't care so much. Then in that type of system, FSK is so good, for this type of transmission. But for a system where bandwidth is important because it's expensive, you want to optimize bandwidth, and you want to send to many users and all that, which is the typical commercial communication system. In this system, PSK is super important. PSK or QAM, they are very useful. Okay. Last example, I think I don't have time, but so you can work as a homework on this problem. Okay. The problem says that if you need to design a communication system, let's say through your watches that can accommodate 9600 bit per second, and bit error rate is less than 10 -5. Okay. Say that if the bandwidth available is only 2400 hertz, SNR available is 8 dB, what would you choose between 16 FSK or 16 PSK? You can use the table on the previous page to compute. Actually, wait, I can do it quickly. I don't need to compute so much. Data rate is 9600, right? This RB. But W is 2400. So eta is equal to 3, right? So if you take a look at the table before, what would you choose if you have eta equal to 3? You have to choose something like this. Yeah. Okay. Because you cannot do it with FSK. FSK has worse spectrum efficiency. So you go to this thing. So you go with 16 PSK. So you choose 16 PSK. Okay. So you can use the spectrum efficiency as one way to select as well. Okay. But in here they say the available bit error rate SNR is 8 decibel. So we use the spectrum efficiency to choose modulation scheme first. And then for SNR, let's see whether it's enough. Well, but now sadly, for 16 PSK, you require at least 13 decibel in the system, okay? But because you require 13 decibel in the system, okay? However, here you only have 8 decibel. So what do you need to do? Well, um, can you go to 32 or 64 PSK? If you look at this table, can you go to uh, oh, sorry. This is 8 PSK. So instead of doing this, I go to here because the question asks whether you want to go to 16 PSK or 16 FSK, right? So uh, they says because eta is here, eta is 3, but the question asks whether you go with 16 PSK or 16 FSK. So you have to answer 16 PSK with eta equals to 4. Okay. But in the system, it requires 17.5 decibel in the system to reach this bit error rate. Okay. However, you only have 8 decibel in the system. So it means we need to use what is called error correction codes in the system. And you learn this during next lecture. Okay. So in this system, you use modulation scheme, okay, to satisfy the spectrum efficiency, but for bit error rate, you don't satisfy yet. So now you have to use some type of error correction code scheme to help. Okay. So please wait, and that's the end of the lecture today. Okay. Any question on this part? I think I went through quite slowly, right? But it should be quite clear what we have been doing all along, right, for the whole